Welcome to Advanced Data Analysis 2 with me, Erik Erhardt, Professor of Statistics at the University of New Mexico. In this video, we'll be introducing Assignment 04 from Chapter 2, An Introduction to Multiple Linear Regression. And this assignment will be similar to Class 3, so I hope you have done that one already, because it will rely on those concepts to do the Class 4 assignment. So here we are in the timetable. I'm going to download the R Markdown file into the ADA2 folder. Now I'll download the dataset, and we'll go over to RStudio. Open that file. Let's see, I've got it in the desktop ADA2 and Class 4 RMD. Open it up. And we will, let me do this first. Set the working directory for the session to the source file location. Then if we run any parts of the analysis in the console, it will know where to find the data. And if there's any output to write, it will put it in the correct place, and we'll knit this document. After this knits, we should get the same document as what's in this HTML file. So I pressed Control and I clicked on the HTML. It opened it into a new tab, and we can start reviewing the assignment. So the story of this data set is a production plant cost control engineer is responsible for cost reduction. One of the costly items in his plant is the amount of water used by the production facilities each month. He decided to investigate water usage by collecting 17 observations on his plant's water usage, as well as other variables. So the water usage, this is the response variable, and we'd like to be able to reduce the amount of water used each month. It's in gallons. The other variables we have are the number of people who are there each month, and apparently this changes from month to month. The number of days that the plant operates each month. The amount of production, and maybe this is in millions of pounds. And the temperature, presumably the outside temperature. All right. So we read the data set. We library the tidyverse to get the functions for data analysis in here. The ADA functions.r script is sourced in order to load the function for diagnostic plots. We read the data set in, it goes into dat_water, and we've got those variables that we just discussed. This actually does not look like a lot of water to me, 3,000 gallons. I think some households might use that in a month, but maybe this is even specific to even a particular process. Okay, we've started by adding an ID column. So mutate variable will create or modify a variable name, and 1 to n parenthesis is the number of observations. So it's putting a vector from 1 to n into a column called ID. And it also has a comment here about filter to remove observations. So later on, if we find that we have some influential observations or some issues, we can use this ID variable to remove certain variables. All right, here is the rubric, and this is the assignment. Complete all these points. There are 8 parts. 2 of them have 2 points, and so there are 10 points total. First, plot the scatterplot matrix and interpret it. Fit the model, the multiple regression, and assess the model assumptions. Interpret those added variable plots. If there are model assumption issues, then say how you are addressing them, and then come back up to the beginning, or say how you address them at the beginning, and then start again. Okay, so for example, you might say, where's a good place to do this? I guess it's probably right here in the mutate. So you'd maybe make some comments that says, there are influential observations, so I removed 1 or 2 of those, or I needed to transform a variable, so in this mutate statement, I added a variable that was like temperature squared or something like that, or log of temperature. Okay, and then you run the whole thing again. All right, and then you then assess the model assumptions again, and so on, right? So iterate, do this as many times as you need to until you've got a model that fits the model assumptions well. Once the modeling is done, then the only thing left to do is to interpret what you've got. So state and interpret the regression tests, interpret the regression coefficients, interpret the multiple R-squared value, and then give a summary in just 1 or 2 sentences. All right, ready to get started? Yes, Eric, we are. Okay, good. So I think the way I've organized this is in section 3 are the solutions, and I think I've got one of these subsections for each of these 8 parts. So at this point, I think I'm going to move away from the HTML view and go instead to the RStudio view and start running code and analyzing it here and writing up. I probably won't be doing a lot of the typing for the interpretations because I don't have to do the assignment, but I will discuss the way I would interpret many of the results. All right. So here's the first code chunk. I'm going to press play here to load the tidyverse, load in those functions, read the data, and we've outputted the structure of the data in part of the output up here, and then we also did this mutate statement for dat water. So why don't we at this point just look at the structure of dat water. And one thing that I don't like that much about the default tidyverse read data, I guess it's in the tidyr package or the readr package, is it creates all these attributes that tells you how the variables were read in. It interpreted the temperature variable as double precision, which means a numeric variable. All of these were numeric variables. There's a way to strip the attribute out of there, but I typically don't bother. Anyway, it just means you need to scroll up a little bit more to see the basic structure of the data. We have 17 observations with 6 columns. These are the names of the columns. You can see the ID column there is new, and you can see how the first 10 observations are counting all the way up to 17. There's the 17 observations. So things are looking good so far. We'll scroll down a little bit. All right, I do have a note here. Because of the high correlation between production and persons, and we'll probably see that in this scatter plot in a moment, we're not going to include persons in the model, but just focus on production. So this sort of could make sense, right? If the number of people you have, for each additional person you produce more, then those things are going to be correlated. So we're just going to focus on production. All right, there's the rubric, and here's our scatter plot matrix. So notice that I've got the select statement. So I'm going to do GG pairs when we just run this and take a look at the output. It should produce a plot over here in the bottom right. And I'm starting with the water, but then I'm selecting which columns. The minus sign means that I'm removing that column prior to running the GG pairs function. So I'm excluding the ID variable and I'm excluding the persons variable. And that gives me just the variables that I'm interested in. I'll make this plot window a little bit larger. Now water use is the response variable on the y-axis here. And as I look across, I'm seeing not really linear relationships with temperature. It seems like there's an increase at some point. Temperature is water use is low until the temperature gets up to about 70 or 80, and then there's a few days when the water use was high. It looks like there's a bit of an increase here with production, and for days number of days the plant was open, it looks looks pretty flat or possibly negatively correlated. The correlation values are on the opposite diagonal, so yes, days and water use. This plot has this slightly negative correlation. Production was positively correlated and temperature not really. Looks like there's not really strong correlation between other pairs of variables. This is very lucky for us because it can be problematic to have correlated X variables within a regression model. Okay, I am also showing you this other type of plot called a parallel coordinate plot, where each variable is here on the x-axis, and each variable has been scaled from its minimum at 0 and maximum at 1 to follow along here. And this is sort of helpful to see if there's like clusters or common behavior. It looks like there's there's a whole bunch of points that sort of start with low water with moderate production where there's lots of people, and then it sort of split, that group sort of splinters. Some go up high, some go medium, some go low. So anyway, it's just another way of visualizing multivariate data. In this case, and I've also color coded the lines based on their water use, based on this first variable. This tends to be useful for clustering and other visualizations of multivariate data. Okay, I mostly just wanted to show it so you've got that in your toolkit. Okay, so the solution here, let's see what we're answering here. Scatterplot matrix and interpretations. So in a scatterplot matrix below, interpret the relationship between each pair of variables. Okay, so we'll sort of go through each of these 6 plots, and I've sort of already done that in terms of what's correlated and what's not. If transformation is suggested by a plot, so because there's a curved relationship, so this looks a bit like a curve, but I don't really see a transformation that's going to straighten that out. Also, plot the data on the transform scale if a transformation is necessary, and perform the analysis on that transform scale. Okay. Otherwise, just indicate that there's no transformation necessary. All right, so I would say that there's no obvious transformation necessary, and that there aren't strong correlations. I would certainly note this one between water and production. It seems like there's a positive relationship there. Okay, so that would be where this answer is here. Type your answer there. All right, multiple regression assumptions. So now we're going to, below the multiple regression model is fit, start by assessing the model assumptions and interpreting. Does this only have one T? I always do that. What you learned from the first 7 plots, okay, and don't do the added variable plots until the next question. If assumptions are not met, then we're going to attempt to address those violations of model assumptions, and then start again. All right, so here is the linear model function. We've got water as the response variable, we've got temperature, production, and days as the x variables, and we've got the data. All right, so we'll run this. Notice I'm not plotting the summary quite yet. In my own work, I would typically plot the summary right away, but then also do the diagnostics right after that. Sort of for pedagogical reasons, I'm fitting the linear model, and then we'll look at the regression model assumptions right away. And then once we're satisfied with the assumptions, then we'll look at the interpretations. All right, so then we create our plots. And this one I probably will jump over to the HTML because it's a little bit easier to look at. I don't know, this is fine. We can do it here. All right, let's go down to, all right, here are the 7 plots. So you're going to fill in after each of these, fill in your answer for your interpretation. Let me take a quick look over at the output here. So I think 7 plots was sort of an old version. I've got 8 here. we can sort of ignore the Box-Cox plot here at the end. So we'll focus on the first 7. All right, I will go back to R. So I don't know, maybe it is a little bit easier to look at here. Okay, so here is the QQ plot. It tells you about whether the residuals are normally distributed. Residuals are normally distributed if they follow this blue diagonal line and they don't really fall outside of these dashed bands. These residuals look totally beautiful, so looks like normality seems to be met. For Cook's distance, this measures the, right, so that's what you would write for that first interpretation. Second plot, Cook's distance, this measures how much influence any individual point has on the fit of the model, meaning the regression coefficients. That's what I mean, the values of the regression coefficients. And it looks like 16 is about twice as high as any other. So it looks to me like we want to maybe think about 16 as being maybe a little too influential, and we might want to see what the interpretation is with observation 16 and then remove 16 to see whether our conclusions change just based on this one observation. Of course, we don't want our conclusions, the inference from our model, to depend too strongly on any single observation. So that's the reason for removing an observation to assess its effect. If we ask why is a point influential, so here's observation 16 up here with the high Cook's distance value, it is because it has sort of a large leverage. So it's a bit of an outlier in the x direction. It's unusual in terms of the x value, and that's why it's having an influence. All right, in terms of the other residual plots, I don't really see much structure in this particular plot. I'm not really taking this line. You know, this line sort of serves as a guide, but I don't really see much structure here. This looks pretty flat. It's so interesting why it decided to connect the dots here, but I also don't see much structure here as well, and none really here. So I think in terms of the residuals versus the fitted values and any of the individual predictor variables, temperature, production, and days, it looks like model assumptions are met. There's no systematic structure to these residuals. There's no curvature. There's no change in variance. So it looks good. This Box-Cox transformation seems to suggest that we want to do some transformation, a power transformation where the y variables raised to like the -4th or 5th power, but our other plots don't suggest anything other than leaving it the way it is. So everything sort of looks pretty good. The added variable plots are really showing how 16 is sort of this high outlier in each one. So it suggests that 16, same thing right here. 16 had the highest predicted value, the highest fitted value, and also one of the highest residuals. So 16 is unusually high. So this is what I'm going to do for the purpose of this assignment, is I'm going to remove observation 16 and see whether we end up with a model that doesn't have any issues. So I'm going to go back to the R code. I'm going to make my editing window large again. And by the way, if you do make this plot window too small and you try to make a plot, you'll sometimes get some error messages about margins being too big. And if you get a margins too big error, it's because your plot window is too small and you just need to move your borders here so that you give the plotting space enough space to fill in some of these plots. Let's see if I shrink this way too large. Okay, there's margins too large. You would also get the error down here in the console. In fact, why don't I just try that right now so you can see what that error looks like. Yeah, here we go. Error in plot new. Figure margins too large. So that error is because this plot window is too small. Make this plot window larger, run it again, works just fine. This error is sort of left over from the previous time it ran. There we go. All right, so let's do this, removing this observation. So we saw that it was observation 16, and I've got this piece of code here that says if the ID is in this list, in this case it's number 16, then this exclamation point says do not include it. So we're going to run this chunk of code again, which will read the data set in fresh, and then create this ID variable, and then if the ID is 16, remove it from the data set. Okay, so now we'll scroll down, we'll run the other parts. Here's our pairs plot. Now if you got a really good memory, you'll be able to see which observation was removed. If you have a lousy memory, like I do, you'll cheat and bring up another plot, as a comparison. Now we know that the predicted value is one of the larger values. Let's see, I'm having trouble grabbing the corner because there's other things going on my screen. Let's see if I do this and this and shrink it down a little bit. Aha, so this big observation here, the day when they used 4,500 gallons of water, that was the influential observation. That's the same point here, the same point here. It also had the day with, what's this second variable? Production. It had the most production and most water use. Okay, and it was, in terms of days, wasn't particularly a month with, it's sort of an average number of days of production, but it was also one of the hottest days. This first variable is temperature, and that's one of the hottest days, had the most production. So, all right, so we're removing, so now at least we understand what observation we removed and why it could have been influential. All right, so we plotted it. I'm paging down, paging down. All right, we're going to refit the model and redo our diagnostic plots. And let's sort of page back to the beginning. Still, the residual plots, or the QQ plot, looks great. Look at the Cook's distance. No observations, much more influential than any others. That looks great. Because there's nothing really super influential, the leverage Cook's distance plot isn't that important, but there's also no more points with a lot of influence or a lot of leverage. So no big outliers in the X direction. All of these residual plots look just great. Yep, everything looks good. So I'm quite happy with removing that observation. For contextual reasons, I would say that we had one day that was the hottest day with lots of production. We used a lot of water, and it doesn't necessarily reflect sort of average operation. So that could be a justification for this study to exclude that observation from influencing too greatly our model fit. All right, so here is the model fit again. I think I've got it down here sort of as a second fit. Wait, what? Let's see, sorry. Maybe I just didn't jump. I didn't go down far enough. Okay, that's the original model fit. The diagnostic plots. We've discussed all of these. Added variable plots. So this is answering the question. Well, let me just read this first. Use the partial regression residual plots, which is another name for the added variable plots, to check for the need for transformations. It also tells us whether or not a variable is important after adjusting for the other variables. If linearity is not supported, then address and restart at the beginning. So let's take a look here. So originally observation 16 was influential, and it's been removed and it doesn't really show up here. Now it looks like observations 6 and 15 are sort of a bit of an outlier. in terms of being far from this regression line. We have a positive relationship with temperature. So others, so in this first plot, we've got water and temperature. The set of variables in others include production and days, the other two x variables. So first we fit, so the x-axis here is the residuals after you fit temperature as the response variable onto production and days. And so this is the way you do interpret these residuals is it's the information in temperature, or the variability in temperature, that wasn't explained by production or days. Similarly, for water, you fit the regression with water on production and days, those two other variables. And this is the residuals here is the variability in water that wasn't explained by production or days. And so now we're asking the question, is there still a relationship between temperature and water after adjusting for production and days? And there's a positive relationship here, and so there looks like there is some information. Now there's these two observations up here seem to be the two observations that are driving the relationship, but nonetheless that seems to be the case. So we want to be a little bit careful that these two observations don't have too much influence on this regression. Sort of similar here, this slope looks like production and water are still related after adjusting for temperature and days. Again, observations 6 and 15 seem to be making this slope steeper than it would be without those two. And then looks like there's a negative relationship with days and water, that the more days there are, the less water use after adjusting for production and temperature. So that's interesting. So it is a conditional relationship. It's after you adjust for production and temperature. Of course, the more days there are, I think we looked at the scatterplot matrix. The more days there are, is there more water use? Well, I'm not sure. Looks there is a slight negative correlation here, so I guess that's sort of suggesting a decrease. And that decreased relationship continues to hold even after you adjust for production and temperature. Okay. So I'm keeping my mind on observation 6 and 15 because those seem to be influencing the fit here. If we go back a little bit and look at the Cook's distance, 6 and 15 are the next two most influential observations. But based on this Cook's distance, individually, they don't seem to be that much more influential than other observations. Now, recall from the notes that Cook's distance is a measure of influence for a single point. But 6 and 15 seem to be co-conspirators. They seem to be working together to influence this regression line. And Cook's distance doesn't measure joint influence of multiple points. But anyway, so I guess what I would say here is, well, write down some of the stuff I already said, that, you know, the relationship between temperature and water continues to be positive even after adjusting for production and days, and say something similar for the others. And you might point out observations 6 and 15 as possibly being jointly influential in this relationship. All right, let's resize these windows. And, all right, we look at the summary. So we've got, all right, state the hypothesis test and conclusion for each regression coefficient. So that is, in this table of coefficients, we've got temperature, production, and days, and each of them has a p-value for whether or not that variable explains a meaningful amount of variation in the response of water after adjusting for the other variables. So in this case, you know, so the I think I might get you started with this answer. Let's go take a quick peek. Page down to this part. Okay, so I'll get you started by writing the beginning of the first conclusion. Each hypothesis is testing, conditional on all other predictors in the model, whether the addition of the predictor being tested explains significantly more variability in water than without it. Okay, so after adjusting for production in days, is temperature important to explain the variation in water? So the null hypothesis is that the beta coefficient for temperature equals 0. The t-statistic is 2.3. Wait, is that true? That is 2.3? Oh, you know what? It's not, because we removed an observation. Oh, hold on a second. You can't look up there because that's before we removed our observation. So let's take a look at this. This is better. So anyway, that's the only thing I need is this. The t-statistic is 1.5. The p-value is 0.14. Okay, the p-value is greater than 0.05. So we're consistent with the null hypothesis here. So I would say the t-statistic is 1.5 with an associated p-value of 0.14. Thus, we, and I've put in brackets here what the decision is. In this case, the p-value is large, so we fail to reject the null, concluding that the slope is not statistically significantly different from 0, conditional on the other variables in the model. And you'd go through and do that for the other ones. Now, I believe that I filled in this t-statistic and this p-value automatically using some R code. Okay, so here, I think, yeah, so I've sort of used older style syntax, but I think it's just fine. We look at the summary. Okay, the summary gives us that big table that we made. Within the summary object, just sort of to help you remember this, you can look at the names of an object. In this case, we're looking at the names of the summary object of the linear model, and it has these objects in it, and coefficients is one of them. So we can look at coefficients. So the summary $ coefficients, what's that? That's that table of the coefficient values. Now the t-statistic for temperature is right here. So that's the second row. The intercept is the first row, temperature is the second row. So there's 2, the second row, and I've got the third column there. Estimate is 1, standard error is 2, t-statistic is 3. So if I highlight that section and press Control Enter, it should give me that number right there, 1.54. All right. The last part is I wrap this with signif, and in modern days I've been sort of following the tidyverse a little bit more, and I would say, and then go to 4 significant digits. Either way gives you the same results. Okay, so I just cut off because humans have trouble interpreting numbers beyond 3 digits, and so 4 gives you slightly more resolution in case you needed it. All right, so then how would I get the p-value from that same table? Well, the p-value for temperature is the second row, but the fourth column. So I'm going to press the up arrow to recall the previous statement. I'm going to put in the fourth column here, and I get the 0.148. Okay, and that's what this code is here. So so I would just modify, take this text and take out the stuff that doesn't belong. Thus, we fail to reject the null hypothesis, concluding that the slope is not statistically significantly different from 0, conditional on the other variables in the model. And then I've got these ... I would copy this, paste it down here for each one, and just fill in what you need to. Now for production, right? So we saw this summary here. If we print out that coefficients table again, oops. we go. We've got, next one is production. Production is the third row. So I just need to change the second row here to the third row. Same thing down here, second row to the third row. And that will give me the correct values for production. Okay, so there's the t-statistic for production. And then the p-value for production is in the fourth column, 0.018. Okay, so it works just fine. Now, just one comment here. You may have seen that, like, hey, there's a lot of digits here, more than 4. That's because this is significant digits, not rounding. And the 4 significant digits sort of starts where the first non-zero value is. If you wanted instead to round this to 4 places, then round would round it to 4 decimal places after the period. Okay, that is all that. All right, next, the multiple regression interpret coefficients. Okay. Okay, so what does that look like? It looks like I get you started here too. That's nice. I'll get you started by writing the beginning of the first conclusion. Might as well jump over to here. Okay, the coefficient for temperature is estimated at, notice I've got beta hat now, because the hat indicates that this is an estimate of the beta value, equals 15.23. Now 15.23 is we know how to get that. If we go to the coefficients table, 15.23, well, this will change once once we rerun it with the new with that observation removed, but it should be 10.16 now. But it's the first column, and that's what we see here for the indices. Second row, 1, 2, first column for the estimate. Okay, so the beta value is estimated as 15.23. Thus, we expect the water to increase, that's the response variable, to increase by 15.2 for each year, that's not quite right, for each degree increase in temperature, holding the other variables constant. Okay, so fix my typo there. So for every degree of temperature that we increase, we expect the response to increase by 15. And interpret those for each of the other ones as well. Now, at this point in the course, we're not yet doing model selection. We're not saying, we're not going through the process of saying, well, it looks like days didn't explain a significant amount of variability. Therefore, we're going to remove days from the model. We're not doing that yet. We will do that very soon, but we're not doing that yet. We're just interpreting the model fit that we have. Okay, I think the next part is the multiple R squared. Looks like it's, around 60% at least before we remove that variable. Let's interpret it down here. I'll bring up the summary again. So the summary without the coefficients. All right, let's take a look at that summary. Okay, once you remove that one observation, observation 16, R squared drops to 40% or 41%. Okay, so that's the interpretation for the multiple R squared. You'd say something like the regression model with temperature production in days explains about 41% of the variability in water, the response variable, over and above the grand mean for water. 40%, that's not too bad. Oops. Interpret multiple R squared. Did I skip something? I feel like I skipped something. Like the, oh no, we covered that. Okay. Summarize your findings in one sentence. All right. So what would that sentence be? So I would just sort of think back to all the steps you took. Something like, after removing influential observation 16 that had the highest water use with very high temperature and production, there was a significant positive linear relationship between water and production, but not for temperature and not for days, explaining about 41% of the variability in water. That's a pretty nice sentence. Yeah, so I sort of talked through the whole process and gave the main conclusions. If you'd like, you can add a second sentence that says model assumptions for the multiple regression were met. All right, that is everything for this assignment. I made a couple changes. I'll go ahead and knit this. This is not, you can end the video now if you like, but I'm just want to see that after having removed observation 16, that we're going to get the correct results that we saw in the console. So I'm paging down a bit. There is where I remove observation 16, and then I'm going to page down a bit. We don't see that outlier in our scatter plot. I page down a bit. We don't see observation 16 as a troublemaker in our Cook's distance anymore. I should make a point here that the observation number here is based on the observation that is just an index of all the rows that appear in the data set that were used to fit the model. Notice that there is a value 16 here, but this is actually observation 17 from the original data set. So this strategy of using the ID number iteratively, say if you were to remove one observation and then another observation and a third observation, this could be hard to figure out which observation number is the troublemaker if you've already removed a couple. So I just state that in a way we sort of wish that this Cook's distance plot had a different labels here at the bottom, or there was a better way to figure out what the row number or ID number is in the original data set based on these labels. But I have not, in all my years, come up with a very good strategy for that. All this looks good. Here's our 41%. So our output reflects what we saw. That was just the double check there. All right, that is everything. I think this last little plot here at the very bottom. Oh, you know what? Yeah. Anyway, that's not too important. This isn't important either. I created these three bivariate plots with this third axis of the color bar to see what the relationship is between temperature and water, and then I put production as the color bar, and as if this was helpful to provide some additional interpretation. You can see why days was not a significant predictor. Let me page up for just to remind myself. Here we go. The main one that was important was production. Temperature was not important, and days was not important. If I page back down, we see production has sort of this strong relationship, but both days and temperature are sort of horizontal. So at least, on the pairwise relationships, that seemed to hold in the marginal or in the multivariate, the multiple regression model. The last thing I want to look at is in the added variables plot. So production was the one that was significant, and this slope is a bit steeper than the other two. And so after adjusting for temperature and days, production was still had a fairly steep slope with water, and that is effectively the relationship that we see in the regression model. When we see that we've got a small p-value here and with a positive slope, that says that that's why production is important, that it continued to have a steep slope even after adjusting for the other variables. For days, it's sort of horizontal, and for temperature, it's sort of horizontal. It's not as steep as this one. So we can get a clue, at least in these added variable plots, that whether or not a variable is going to be important after adjusting for other variables. I think that's everything I want to say. I hope this introduction was helpful, and I'll see you in the next one.